It's 10 o'clock. We can start maybe.
So, Francesca, just let me know anytime you want to start.
Yeah, I think we can start. I see 64 people on YouTube waiting, so we can start now.
All right. So then I would like to welcome everyone who is attending this online event. This is part of the celebration of European Researchers' Night that takes place usually at the last Friday every September, but there are also pre-events the day before. So today is such a pre-event. We want to give the opportunity to everyone to be able to remotely visit a very large infrastructure, research infrastructure like Virgo that has participated in historic scientific discoveries. And so before we start, let me just for a few minutes give some information about what is the Pico project and what we are organizing tomorrow, which is the main day of the Researchers' Night. So let me share a presentation. Okay. Okay, so I think you can see now my presentation in full screen. Yes. All right. So Pico project is physics for all. It is a project with the aim of communicating to the public the modern advances of physics and the applications in everyday life, but also to bring the subject of physics closer to students, and also the subject of astronomy closer to students. And we do this not only by organizing the European Researchers' Night events in several different countries, but also throughout the year, we organize many events at schools. So we are visiting schools and give lectures and talk to students there, but also students and whole schools are visiting large infrastructures are visiting astronomical observatories, either on-site or remotely. So in this project, which is funded by the European Union, institutes from 4 different countries participate. There is Italy, Greece, France, and Spain. And more specifically, the institutes are the Aristotle University in Thessaloniki, the Institute of High Energy Physics in Barcelona, CNRS in Paris, the communications company Trust IT, the Institute of Nuclear Physics in Italy, the European Gravitational Observatory also in Italy, and the National Astronomical Observatory in Athens, and Ελληνογερμανική Αγωγή, which is also in Athens. So these are the participants, the partners in this project. And for detailed information about our activities throughout the year, but also those that will take place tomorrow in different cities, please visit our main website, which is picoproject.eu, and there you will find direct links for the organization of the Researchers' Night and all details where it will take place, what exactly is going to be displayed, and what times you can visit. You find direct links for each different country. So I don't want to take too much time because we want to leave time for your remote visit to Virgo, but I will spend only a couple of minutes summarizing the different events that will take place today and tomorrow. For example, in Italy, at Cascina, there will be tonight an event at the parish church of Saint Hippolytus, called the Craziest of Enterprises. And tomorrow there will be guided tours of Virgo during bright night. In Pisa, there is an event, Women at the Frontier of Knowledge, taking place for students at the Fibonacci Comprehensive Institute. In Milan, the main event organized by Pico is called The Hidden Music of the Universe, taking place at the Leonardo da Vinci National Museum of Science and Technology. And in Rome, the Big Bang machine that is displaying several aspects of general relativity and gravitational waves will be there for you to visit on Friday and Saturday. Then going to France, the main event for the Researchers' Night will be organized tomorrow at the Grand Moulin University Library. There will be several interactive workshops at the ground floor, and there will also be 3 different talks for the general public taking place in the second floor of the museum. In Spain, there will be a Researchers' Night event organized by the Institute of the High Energy Physics. Please visit our main website that I showed the link before for full details on this event. And finally, in Greece, there will be several Researchers' Nights events organized in different cities. In Thessaloniki, it will take place at the Science Museum Noises, starting at 5 p.m., where we will have many research groups from the physics department and also student groups displaying their current research with interactive exhibits. And in Athens, similarly, there will be large events for the general public organized by the National Astronomical Observatory in Pendeli, where the main observatory is, and then also at the center of Athens in Thysio at the historic side of the observatory, and also in Pallini at Ελληνογερμανική Αγωγή, who also have a telescope there. And finally, in Corinth, at the observatory, there will be also an event for the Researchers' Night organized. So this was the summary of what is taking place this year. We hope that the public will enjoy it. We are very excited to welcome everyone to these events, but I should not take more time than this. And now, Francesca, please, you could start with a virtual tour of Virgo. Thank you.
Thank you, Nico. We can start then with the guided tour to the Virgo interferometer.
Can you hear us?
Yes.
Okay, perfect. So good morning. My name is Julia Casanueva, and I am at the moment at the European Gravitational Observatory, where Virgo experiment takes place. So I'm a physicist working in the Virgo experiment, and I will try today to give you some hints of how it
Julia,
works.
sorry to interrupt, but on YouTube, we can still see Francesca.
Our camera is working, so I don't know if it's how does it work. Because we are streaming from my account. Is that the problem?
No, it's working. It's working.
Okay. You tell me when you see us.
Okay, I can see you on YouTube, so I think it's fine.
Okay. So I would say, as I was saying, I will try to give you some hints to try to explain to you how it works while we show you a bit of the facility. So before we start actually showing you things, I need to, let's say, explain to you why we build such a huge facility. So Virgo detects gravitational waves. And the history of gravitational waves is quite old, because it has already, it started with Einstein in 1916 with his general relativity, where he tried to actually explain, not just describe gravitation as did already in the 17th century. So Einstein tried to go further and try to explain why, not just how they moved, but why they moved like this. And he came with this idea, which was kind of revolutionary, because he imagined space-time as a whole, as an entangled thing, and he imagined that everything is in this tissue. Space-time is a tissue which is flexible. So, for example, the sun is very massive. So you can imagine actually a tissue, and when you put something that's heavy, the tissue will bend. And such we do space-time. So the idea is it's kind of it seems abstract, but actually it actually makes sense. So the Earth is actually moving forward. It's not like actually making circles. It's the space which is actually bent. So the Earth going, straight line, but it still it's trapped because the space-time is so curved by the sun that we are trapped turning around. And he said this is the way it works, everything in the universe. So anything that has a mass will bend more or less the space-time around themselves. And that's how actually massive things interact. So they interact to this fabric of the. And gravitational waves are just as any other wave that we can think of. The easiest example is when you throw a stone on a pond in water, and that it will make some waves too. So this is exactly the same. So massive objects moving will actually create ripples, waves in the space-time, and they will propagate. Luckily for us, these ripples are tiny, but they interact very faintly with matter, which is quite different from photons, because typical observatories, like magnetic observatories, have the downside that photons interact a lot. And if you have, like something between you and the source of the light, it will never arrive to you. But gravitational waves, they interact very faintly, so they will travel for long distances before actually losing energy. So Virgo is a detector beam to wait for this gravitational wave to pass to us. And so now that we more or less understand what are gravitational waves, we can try to explain how we build a detector for gravitational waves. So here we have kind of a model, a small scale model. I will here. So basically, what we want to measure is how the space-time is disturbed by gravitational waves. So in practice, it means that we want to measure a distance between two objects that feel gravitation, and if a gravitational wave passes, the space will change, or it will kind of grow, increase, or it will decrease. And that's exactly what we want to detect, a different change in the distance between these objects. And so it turned out that there was already an idea which is called the Michelson interferometer. Physicists, we love to put our names in it, right? So Michelson was the first scientist physics, and the idea is that we use light to measure these differences. So Michelson interferometer is what we have here. This is a typical experiment where you have a source of light. In this case, we have a visible light, and then what we call a beam split. So prisms that will divide the beam in two identical beams, and each one of those beams will travel along in this case, Virgo is 3 kilometers long. So this is just a small setup, but the Virgo arms are 3 kilometers. So it's one of these beams will travel around a different path, and at the end they will find a mirror and will send them back to the same place where they split. And when they will recombine or interfere, why we call it interferometer, basically they will exchange information on the travel they did. So our work as scientists is to keep the distance exactly the same between the two arms, so that when the beams will interfere, they will exchange information, and if they have traveled exactly the same path, they will make what we call destructive interference. So basically, if we if you imagine waves as like having ups and downs. So basically, whenever both arms have traveled the same distance, they will be perfectly in opposition. So the maximum of one will be in agreement with the minimum of the other, and the sum will be 0, which is why we call it destructive interference. So we wait with the arms exactly at the same distance, so that this interference is always 0. However, when a gravitational wave will pass, then they will be slightly different, the length, and the maximum of one will not be in agreement with the minimum of the other, and the sum will not be 0 anymore, and there will be light at the out of the detector.
Excuse me.
Yeah.
There appears, according to the comments from YouTube, there appears to be a problem with the sound. Maybe if you could have the microphone a bit closer. Thank you very much.
Yeah, I can. Yeah. Wait a second, we have also a problem with the holder. But it will, yeah.
Okay.
Okay.
Thank you.
Now it's better?
I think
Can you
so,
hear us
yes.
better?
I
Yeah.
think so, yes. Thank you.
Okay, perfect. So basically, in Virgo, we wait in the dark, if you want, until a gravitational wave passes, and a gravitational wave will create light. Because, you know, these two beams will be slightly spaced. So basically, we use time to measure this difference of distance, which was it's a bit the intuitive thing to do when you want to measure distance is take something actually physical to measure. But since everything is embedded in the space-time, what we use is light, which in principle is not sensitive to gravitation. And what we do is we use the time it takes to light to travel, because light always travels at the same time. So if you want, we can show you now the tricky part of this screen. Because you know, basically we tune our interferometer so that we have an interference. So in the screen you see the spot of the laser. The whole problem is that you can see that it's moving a lot, and I can even, you know, even the beams might. So basically, the whole problem that we need to solve that when I build a detector which is very sensitive, you okay. So when you have a detector that is very sensitive to everything, you cannot choose. So when we build a detector that is able to detect gravitational waves, which are tiny, you cannot choose what you are sensitive. So basically, if I'm close to the detector, I will disturb it. The movement of the Earth will disturb the detector. Flames, earthquakes, everything basically becomes a noise. So the difficulty once you come up with the way with the detector, like how the physics, the principle of how it works, is actually to isolate your detector from everything that is not interesting for us. So everything that's not a gravitational wave, we want to, let's say, remove it. So this is why we need such a big facility, because as I said, Virgo has 3 kilometers long arms. But it's not the only technology that actually is very cutting edge. So, for example, the movement of the Earth is disturbing a lot the mirrors in particular, because the mirrors is the place where the beam interacts with something. So, okay, so apparently you're not listening well, so we will try to change the
Can you hear me now better?
Yeah, thanks, Julia, much
Okay.
better.
Okay. 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 So, so I hope you more or less had understood so far. So what I was trying to explain now is how do we actually protect ourselves from the noise that it's not a gravitational wave. So one of the main offenders is the movement of the Earth, which basically we cannot remove. We have to deal with it. So one of the ways to do that is we have suspended all our mirrors in Virgo. But when we say we have suspended, basically we have built attenuators that are 9 meters tall. So so this is a prototype. It's not exactly the same model that we have in Virgo, but it gives an idea of the working principle. So we kind of force seismic noise or the movement of the Earth to enter through the bottom of the suspension, and then it needs to go all the way up 9 meters and then go down through each one of these stages until it arrives to the mirror. So basically the idea is like each one of these stages of the what we call super attenuator, it attenuates a bit farther the seismic noise so that when it arrives to the mirror, then it's much smaller. So actually paradoxically, the working principle of this super attenuator is quite simple because it relies on the simple pendulum mechanism. So it actually has a simple pendulum has a very useful for us mechanism because it has one frequency at which it actually amplifies the movement. So basically, my movement of my hand is very small, but then the mirror, what it would be the mirror, it moves a lot. But above this natural resonant frequency, it is what we call a passive attenuator. So basically, if I move my hand very fast, it actually will attenuate. So the mirror will move much less than the movement I'm doing. So basically, we are taking advantage of this intrinsic property so that each one of these stages is a simple pendulum. So the movement is attenuated by 12 orders of magnitude, which means 0 dot 12 zeros and 1. So by the moment it reaches the mirror, the seismic movement is very small. It is around 1 micrometer, so 6 zeros before the 1. Still, when we are trying to measure gravitational waves, we want to measure a change in the distance of the order of 10 to the minus 18 meters. So it is much smaller than micrometers. So still our mirrors move a lot. So even if we have protected them from the seismic motion, we still have to further calm them down. And for this, we're going to have like an analogic zoom. So here we have, this is more realistic, a realistic model of the bottom part. So these are the two last stages, what we call the marionetta and the mirror. This is one of the old mirrors of Virgo, okay? So it's a real mirror. So basically, what we want is to calm farther down the mirrors, but we don't want to spoil all the work we have done because with these super attenuators, we have already removed a lot. So we don't want to touch the mirror because then if we actually touch it, we will be reintroducing the noise. So we want to be able to act on the mirror without touching. So what we do is we have this cage where we have coils. And yeah. Yeah.
We are asked to repeat a summary of things said when sound was not.
Okay. Okay. So let me finish this, and then you can tell me what do I need to recap. So the coils, what we do is yeah, we have these coils attached to the cage, and we have magnets glued to the mirror, which means that we can use electromagnetic force to push or repel the mirror. So we attract or repel the mirror using a change in current in these coils. So this is the way we have to act on the mirror without actually touching. And we can do this in the sense of the beam, so pushing on the mirror, or we can also orient the mirror from the top, from this marionetta, so that we can tilt it. So this way we have all the, let's say, tools to actually act on the mirrors, and what we do is to synchronize them. So what we look for is not to actually stop them, but to make them move exactly in the same at the same time. So we synchronize on the mirror so that the relative distance between them is always the same. So do you want, so yeah, can someone tell me exactly, do I have to start from scratch? Let me know, what do you want me to repeat? Okay. So, okay. I don't know, we're still there, right? Do you hear me?
Yes, we do.
Okay, okay. So let's say I will continue, and then eventually you will ask me questions. Maybe at the stop, at the end of this, yeah, of this stop, you can ask me things.
Julia, there was a question from the audience
Yeah.
asking if it is possible, after a passion, to repeat, to give a brief summary of the things presented while the sound was not good.
Yeah. So that's why my question. So
Thank
when
you.
you mean, I don't know when the sound was not good, so do I need to start everything, or it's one particular part?
No, I believe a small overview before we leave the room would be sufficient.
Okay.
Thank you.
Okay. Yeah. So so we can come back to the interferometer, which I guess was the part which was.
From the lasers, because you moved away.
Okay. Okay.
Just to give us
Yeah.
quick summary.
So basically, I was trying to explain that Virgo is a Michelson interferometer. So, so basically, this means that it's an instrument that uses light to measure a difference in distance. So a Michelson interferometer, it's an L where we have a laser source, and we have a beam splitter that divides the beam in two identical beams. That they travel different, different paths until they find a mirror that sends them back. And they re-interfere in the point where they splitted. So when they re-interact, they will exchange information about the distance they have traveled. So basically, this interference will be destructive if they have traveled exactly the same distance. And so that's in the state where Virgo works. So basically, we try to keep the distance always the same, so that we are always working in the darkness, so in destructive interference. And whenever a gravitational wave passes, the distance traveled by the light will be disturbed, and then this interference will not be anymore perfect, and there will be some light leaking in the output of the detector. So that's exactly what we are monitoring. So that's basically the main working of the detector. Yes. So now the other thing, so we have discussed already about the seismic noise. which is one of the main offenders. Just to say, basically, the detector has to be very, very perfect, because any, let's say, mistuning has a huge impact, because the gravitational waves we're trying to detect, they are very small. So as I was saying, this is one of the old Virgo mirrors, which was 20 kilos heavy. The one we have now are 40 kilos heavy. Because it's important, because light, there's so much light inside the detector that it actually pushes the mirror, which is why it has to be heavy enough to stay as undisturbed as possible. Another thing that it might seem weird, is that actually we can see through this mirror. So when we think about mirrors, we think about the mirrors we have at home, but actually the light in Virgo is not visible. So our laser source is infrared, which means we don't see it. So when we look at the mirror, it's not a mirror for the light we see. It will be a mirror for our laser, which is 1064 nanometers wavelength. And then there's another detail which might be seen better here, which is how do we suspend the mirrors? So these 40 kilo mirrors are suspended by fibers, which are 400 micrometers diameter. So this is basically like the diameter that would have 4 hair put together. So these 40 kilos are suspended by these 4 fibers, which are very, very thin, but they are super resistant in the gravitational, in the direction where the Earth is actually pulling us. So as you see, even the fibers that suspend the mirror are made like in a very it's cutting edge technology, let's say. So basically, when we try to build Virgo sensitive enough, everything becomes a challenge. So now that more or less we understand, like, okay, we have an L, we have 2 mirrors which are waiting for us 3 kilometers after the 3 kilometers of traveling of the light. Each mirror is suspended by 9 meters at attenuator. We can act farther in the mirror so that we can synchronize it. The mirror is super heavy to deal with the high power. It's suspended by fibers. And now one of the other things that are particular to Virgo is the fact that the light travels in vacuum. And in order to show you better this, we are now going to one of the tunnels. So one of the arms through which the light is actually traveling. So we might lose the connection for a few seconds, but as soon as we enter the tube, the tunnel, it will come back. So just advanced a bit. No, but I think no one has complained. Can you see it? Can you hear me?
Yeah, we can hear you.
Okay, perfect. So we are now in the tube of Virgo. So you can see that it's taller than me. which is not a lot, but still. So what we see here, it's the outer tunnel. So inside this tunnel, there's a tube which is actually where vacuum is done inside. So this is still protection, but the real tube is inside, is around 1 meter diameter. And so we have this 3 kilometers path of 1 meter diameter in vacuum where the light actually is passing at the moment. So we have the beam that's just circulating next to us at the moment. And this vacuum is very important because it's the only way of making sure that the light is actually undisturbed. If we have particles in air, then the light will interact with them. So we make a vacuum, which basically means absence of particles. And it is actually quite tricky to do. So just as a fun fact, we have the biggest volume of vacuum in Europe because, yeah, the CERN facilities have much smaller tubes. And the vacuum in the arms has been done in the late 90s, and it hasn't been broken ever since. So inside the tube, the vacuum is there has been there for 20 years. Because the beginning of the vacuum is very easy. When you have lots of, it's the same, you have to imagine almost as at home, right? Like when it's very dirty, it's very easy to remove. But once you have few particles left, it's much more difficult to actually catch them. So the more vacuum you have, the harder it is to keep emptying it. So actually, we say ultra high vacuum, which means that there's less particles in this tube than in the outer space. So just to give you an idea. So it's really empty. And this basically means it's very clean. So cleanliness is very important for vacuum. And so, for example, when we say clean, so we actually heat a lot the tube once it's here to try to, let's say, speed up the process of all this release of particles that maybe are trapped inside the material itself, or so we basically, once we installed the tube, we heated it a lot for weeks, so that we accelerated this process of releasing whatever residual, particle or dust or water that was still there. And then, so you can see also that every few meters, there's these legs in blue. So basically, this means this is useful for leveling the tube. So we avoid stress, and because in 3 kilometers, we feel a lot the curvature of the Earth. So light travels in a straight light, but this is not the case. So the Earth is curved. So if we have a mirror in the central interferometer that it's attracted to the center of the Earth, this means that whenever we put another mirror at 3 kilometers, it will be also attracted to the center of the Earth. So you have two mirrors that are like this, and the light has traveled its way. So we need to, if we want the end mirror at 3 kilometers to actually receive light, you need to move it up and tilt it locally so that they are actually in parallel, and the light, actually arrives in the center. So now I'm exaggerating, but these legs helps compensate this curvature of the Earth. Without, also it helps, of course, also with, we have at the same time, we have these springs that helps us with dilation, with changes in temperature and so on, so to avoid stress. Also notice that the building itself, every few meters, it has some patches. So the idea of all these, infrastructure is to actually maintain the the environment around the tube always stable and avoiding stress. Because actually, if you think about it, there's not a lot of buildings that are like kilometers long. So we need to actually keep track of these things. Also because Pisa is actually, as you know, probably you have heard about the tower, which is a bit pending. So the floor is not very stable. So actually, we need to keep track of how the floor is moving and compensate if needed. So every year we make topological measurements to make sure that everything is in line. And then there's also, so we have said 3 kilometers. We have vacuum inside, which is why I can be here today, because between me and the light, there's no way of propagating noise. So even if I make noise here, there's no particles that actually inside the tube that can communicate this pressure difference to the light. The tricky parts are the moments where laser meets the mirrors. That's the moment where the mirrors can pollute the beam, which is why we have this attenuation. But if the light interacts with the tube, then it will be all scattered and it won't arrive to the end. So part of the reason why we have a very big tube, it's because we have to have some margin, because aligning a beam 3 kilometers far, it's quite tricky. And if you put a small tube, then you make your life very hard, because you are trying to align the beam so that it reaches, not just, I'm not talking about precision, just that the beam actually reaches the end. You don't see the beam because it's infrared. And so you're not sure even because if it touches the tube in between, it will never arrive. So we let ourselves some margin so that we can explore, so that we can align the laser without, making it hardly impossible. So I think this is basically all I wanted to tell you here. I don't know if now the last step is the control room, but I don't know if you want to make some questions about the detector now. Okay. So in any case, please think about questions about the detector, because now I will move to the control room and we might again lose connection meanwhile we are moving. So like that, I give you some time to think about questions and then.
Julia, sorry.
Yeah.
There is actually a question
Okay.
in the chat box, and is what is the temperature inside the tunnel and inside the vacuum tube? Are they held constant?
Okay, so actually, we don't have, during the tube, along the tubes, we don't have temperature control. It's quite, as if you see the building, it's quite isolated. So now it's kind of fresh. Also in summer, it's kind of fresh. So there's not big excursions of temperature, but there's no active control. Actually, the tube, so the vacuum is a very bad temperature conductor. So that's a nice point for us. This means that once you are in a regime, you have to. So if you want, let's say, inside to notice that the temperature has changed outside, you have to heat a lot. So the natural changes of temperature won't disturb the laser in the tube. It's a bit different in the central building where you have the laser beam, for example. So optics, they are sensitive. So I didn't talk a lot about the laser, but of course the laser source, it's also what we saw at the beginning that was like a pointer, a laser pointer. In real life, the laser has a whole room for for himself, because it needs to be stable in power, in shape, in frequency, in alignment. So we have a full room that prepares the laser to be injected. And that room, for example, it's temperature controlled, because the optics misalign for relatively low changes of temperature. 1 degree might be huge, can have a huge impact. So the central building, so the moments where, the mirrors, the super attenuators, for example, they are like made in metal. So those are more sensitive to temperature. Lately, for example, last week we have had troubles with the active with air conditioning, and for example, the suspensions, they dilate, and then so the mirror moves. So basically, during the tube, it's kind of okay, but the suspensions and the optics are quite sensitive. So in the relevant parts, we have temperature control. It's important. Yeah. Okay, so as I said, please think about more questions, and I will take them when we arrive to the control room. Yeah, so we will lose connection for a bit, but yeah, it's like a couple of minutes maximum. Okay, so let's see if here we can recover. Do we have, yes? Okay, so can you hear me again?
Yes.
Yes. Okay, so I'm in front of what we call the control building, because it's the building where we have the control room. So before we enter, I want to explain to you a bit of how data taking works, because we've discussed about the gravitational waves, what are they, and how the detector works. But we haven't mentioned like why, or what do we actually study now with gravitational waves. So basically, Virgo is an observatory now because we
We have a question.
Yeah.
How many years did it take to build the vacuum?
Okay. So the project of Virgo, let's say, was approved in the early 90s, like 93. And then we started building. So I think the arms were there in the late 90s, maybe 97, 98. But it was, I think it was not until like 2000 when they started pumping vacuum. So basically the pieces were, because it's, as you can imagine, 3 kilometers is very long. So the pieces were mounted in situ. So the pieces were baked, what we call baked, in, you know, wherever they were produced, and then they were brought here. We actually make all the mounting here, and then that's why we made a further cleaning in situ. While once everything was mounted, and we started pumping, and we've been actively pumping ever since. So it's not that we made the vacuum and that's it, because there's always some leaking. It was approved, but it had started already in the mid 80s. And it was not until 10 years ago that the first gravitational wave was detected by the LIGO detectors, and it was not until 2017, August 2017, that Virgo detected the first gravitational wave. So it was 30 years work, basically. So you have to imagine all these people working together, believing that these gravitational waves not only existed, but they could be detected. So basically, it was not until 10 years ago that actually Virgo stopped being a fundamental physics experiment and became an observatory. Because once you know that gravitational waves exist and we are able to detect them, then you start actually studying the sources of these gravitational waves. So in particular, we study black holes and binary and neutron stars, which are the objects that are heavy or compact, what we call like dense enough, so that when they move, they disturb the space-time very significantly, because otherwise I am disturbing the space-time, but it's so tiny that we would never manage to measure it. So basically, we are targeting very what we call catastrophic events. So supernovas, black holes, neutron stars, those are our targets. And so far, we have detected black holes and neutron stars that are in couples, binaries, and that they are moving one around the other, while, you know, and while they move, they lose mass in the shape of gravitational wave, and while they lose this mass or energy, they become closer and closer, and they spin faster and faster until they merge. So we basically detect this last part of the life of the merger of these two objects. So that's what we have detected so far, but we're hoping to, of course, detect much more things, and for that we need to take data. So we have to find a compromise between improving our detector, because we want the more sensitivities, the farther the more volume of universe I can study. But of course, you can have the best detector in the world. If you don't take data, then you won't see anything. So we have to try to find a balance between these two parts. And let's say the control room is where all the work happens in both cases. So whenever so at the moment, in this particular moment, we are undergoing an upgrade. So we have installed we have replaced, I remember I told you that we basically wait in the dark for some light to happen. So there's a photo detector. So there's a detector that actually monitors this darkness or this light if there's a gravitational wave. And we have replaced that detector, so the actual core of the experiment, by a version which is much better, because we expect to improve the sensitivity. So at the moment we are what we call recovering, because like once you have basically each one of the parts we have described, it's a whole experiment on itself. So you have the vacuum, you have the mechanics, you have the controls, you have the laser. And at some point you have to put everything together, and it's not enough just to turn it on. So you have to somehow bring it to the best sensitivity. So it should be easy now because we have just made a small change, but still it takes time to recover the normal functioning. So we take data together with our colleagues of the United States, the 2 detectors of LIGO, plus depending on the period with our colleagues in Japan, Kagra. Basically, the idea is that whenever we are taking data, that we are hoping it to be to restart taking data soon. We have been taking data already for 1 year, more or less, and a half. There's always someone in the control room, what we call the operator, that it's monitoring continuously what happens to it's like a guardian of the detector that is always there and knows how to solve the day-to-day general problems. I don't know, you have to reboot something, you lost some samples of data, electrical or some, control that temperature, that, like the basic day-to-day problems. And we have the experts that are what we call on call. So whenever the operator encounters a problem that is preventing from taking data, quality data, he tries to solve it, and if he can't, he will call the expert. So that's why during the data taking, we are 24/7 working, and each section of the machine has is on call. And then like today, whenever we are actually working on improving the detector, then the control room becomes a working place. So it's there's plenty of people there. So if you have to do something, you have to pass through the control room. So it becomes the headquarters. So everything that's going on, or it happens in the control room, or it has to go through the control room to ask for permission but the control room needs to know. It's like the head of the detector. So it has to know what's going on at any time. And so this means that we built it so that we can see and what's going on in the detectors. You will see now that we will enter. There's plenty of cameras that show the beam. So where you have the beam, what's the shape of the beam, and it is misaligned, it has a weird shape. So this is like information that visually cuts you, like it's very straightforward. We have the screen with all the, let's say, it's very like a color code easy for the operator. Green, yellow, and red. So there's like a summary of all the detector status summarized in squares with colors. So like that, even not just for the operator, but even myself, which I'm an expert of mirror control, I might not realize that the laser has a problem. So each expert has come up with some together some codes that it will pop up red if something is out of the ordinary. And then we have more qualitative signals. We have detectors that actually tells us how much photons are we getting in different points of the detector that are relevant, so that we can understand what's going on in the detector while being away. So this is important, not only because we are an international collaboration, there are people from everywhere in the world working, but also because we cannot get close to the detector, because if I walk close to a mirror, then I will disturb it. So we need to be, we are noise for the detector, so we have to be far. And so we have to know what's going on, and we have to be able to act on it. So since we are in vacuum and you cannot just, go there and move things, we have tried to put motors on everything. So we can change temperature, we can, tilt mirrors, push mirrors, change, the attenuation, the length, the position of the mirrors. So from the control room, we are able to act from remote also on the detector. So let's say the control room is the place, is the head or the heart of the detector, because from there, you know what's going on and you can act on things. So now we can enter. I will show you. There will be a bit of people there. So I will try to be quiet because we are working. So if you want to just, yeah. Yeah, so this is, I will stay here because you can hear me still. So this is the control room. As I said, there's a bit of life because we are actually working on the recovery. So there's people from different, with different expertises actually working. Yes. So as you could see, like at the moment, there's kind of a lot of activity. And so I don't know if, so this is basically an overview of Virgo, how we work here, what's going on. So now it's a good moment to ask me whatever you have in mind that you haven't understood, curiosities, whatever you want, please just go ahead.
I have a question actually. So the question, I saw that the weather is very cloudy outside. So I was wondering, is Virgo sensitive enough to be able to be affected somehow by atmospheric phenomena like clouds, so to say?
No, not to, can we just move like this? Okay, so not to clouds, but to wind, yes, but more like pressure fluctuations, not so much about overall pressure, like, yeah, the like general, but to storms, yes, to wind a lot, and of course also to whenever there's a storm and it excites somehow the sea, that also, for example, it actually pushes into the earth. So more in, let's say, it's a more mechanical way, let's say. So wind directly kicking the mirrors or the buildings and the movement of the earth. The earthquakes, of course, that those are a problem everywhere. So what I mean is whenever there's earthquakes that are like, yeah, above 5, anywhere in the world, it will arrive to Virgo and it will perturb us in a macroscopic way.
Thank you very much. We are waiting for any potential questions from YouTube. Okay, there are no questions at the moment. Let's wait a bit more.
Yeah.
Sofia Kirgiazopoulou says she thanks us very much. Once the sound problem was overcome, it was a very nice presentation. Thank you very much, Sofia. Okay, I see there are no more questions, so maybe it's a good moment to conclude this wonderful presentation. Thank you very much, Julia, Elisa, Francesca.
You're very welcome.
Yeah, Manolis, thank you all, thank you, Julia, thank you all for joining us today. We hope you enjoyed the visit and that it sparked your curiosity about gravitational wave science and the work here at EGO. So feel free to stay in touch, and we look forward to seeing you again at future events within the Pico project. Bye-bye.
Bye.